In this video, we're going to look at another method of generating Gaussian variates. In other words, variables drawn from a normal distribution, from the PDF of a normal distribution. And in contrast to some of the other methods, for example, the central limit theorem method, where we took several uniformly distributed numbers and added them together and then used the central limit theorem to obtain a normally distributed value, at least approximately one of those. We're going to do what we did with the Box-Muller transformation, which is we draw a single value and we do a transformation on it. The Box-Muller method was a geometrical transformation. What we're going to do with the Inverse Cdf method is we're going to use the cumulative distribution function of the PDF for the normal distribution. So Wikipedia is not a bad place to look to find these things out. So we look over here and we see that we're trying to draw samples, say from this red curve, which has a sigma of 1, and that's the PDF. And if we integrate from minus infinity up to each of these values of x, we can see that half the sample should fall below x equals 0 and half the sample should fall above x equals 0. So this red curve here indicates the integral, the cumulative distribution function of that PDF above. Now, imagine if we were to swap the x and y axes of this CDF graph. We have now, rather than having y equals the CDF of x, we would have x equals the inverse CDF of y. What does that mean? That means if we draw samples which have a uniform distribution across this interval here from 0 to 1, and we use that inverse CDF, we convert those y values back to the x values, you can see that a uniform distribution on this y-axis gives rise to samples which are clustered towards the center. And in addition to that, of course, the PDF, the probability of generating samples out in these wings, of course, you see falls to 0, but it has the correct distribution. So samples drawn uniformly along the y-axis and then converted using this inverse CDF function into the corresponding x values are now samples which reflect this PDF above. So how do we do that? Well, we need a formula for the inverse CDF, and it's actually written down here, and it's actually quite close to this quantile function. So we're going to ignore the mu and sigma value, that's the mean and standard deviation. We're just going to concentrate on this inverse error function on the right here, and the fact that we have to appropriately scale that by putting in a uniformly distributed number here and appropriately scaling the overall size, in this case by square root of 2. So how do we actually do that? Well, let's look at it on the left hand side. So I'm going to generate 1,000 samples, n samples equals 1,000, and for simplicity I'm going to loop over the number of samples I want to generate, and for each of those samples I generate a single uniform variate, and then I do a calculation which yields a single normally distributed variate. So actually I'm going to uncomment this line here and I'm going to comment this one out. There are two different ways I'm going to show for how to do this. So you can see here that on the bottom I have done this calculation that I show on the right hand side. Okay, so z equals 2u minus 1, where u is a random number, and I multiply that, I put that into the inverse error function, and when I multiply that whole thing by square root of 2, I have the inverse cumulative distribution function. In other words, this formula here is the formula for the inverse of this red curve on the Wikipedia page. So if I do this calculation, I just save and run, I do 1,000 samples and wait for a moment for it to pop up. There it is. And you can see that I have samples which are drawn from the appropriate PDF, this one above. Let's increase the number of samples just to show that's happening. Make 5,000 samples, so it'll take a little bit longer to run. There it is. Okay, so now it's looking pretty close to this PDF on the right. Now you can see that the advantage of this method is that we only need to generate a single random variate in order to generate a single normally distributed variate. The downside is, of course, to calculate that inverse CDF, there's a complicated computation which is being done inside MATLAB to evaluate the inverse error function. Now, if I want to speed that up a little bit, I can use an approximation. So that's what I'm doing on line 12. So let's comment out line 13, which uses the inbuilt function. And I'm going to use an approximation to the inverse error function, which is given on the line above. And I'm going to use the first, I can't remember how many terms, if the 6 or 7 terms. So I have an expansion which has got terms in z, z cubed, z to the 5th, and so on. And you can see there's some rather long-winded coefficients here, and I go up to z to the 11th at the end here. And so this formula is an approximation to the inverse Cdf. So when I run that, I should get normally distributed numbers to at least some degree of approximation. Of course, there's also an approximation in this function below, but it's probably a little bit better. Now, we run it again, 5,000 samples, and we produce normally distributed samples. But you notice now that because we've used this approximation, this truncated expression for the inverse Cdf, you can see that the samples that are produced don't extend out into the wings as far as we would like. So this central region is sort of normal, but we can't generate samples which are beyond about 1.4 sigma. So if we wanted to do that, we would have to add on extra terms at the end of this formula to improve the approximation of that formula to the true inverse error function, which is below. So let's look a bit closer about why that is. Well, on this script here, I'm just going to do the same thing. I've got these two formulae. I have the correct inverse error function and my approximation to the inverse error function below. Sorry, the approximation to the inverse Cdf, actually. So what I'm going to do is I'm going to run those two calculations. So what I've done is, rather than having random samples, I'm simply plotting out what those two functions look like over that unit interval from 0 to 1, which I've got here. So when I do that, and I compare the two of them together, you can see that in the central region, so this is my value from 0 to 1 on the horizontal axis, and these are the where the samples are going to be generated. So you can see that in the central region I'm generating samples more or less correctly if I use the approximation, which is the red curve, because that curve is a reasonable approximation to the correct curve, which is the blue curve, over about sort of 1.5 sigma or so. But you can see if I were to generate samples out in the wings here, sort of near 0 and near 1, you can see that my approximation is yielding samples which aren't extending out into the wings of that distribution enough. You can see that again, they're limited to around about 1.4 sigma or so. So that's basically inverse cumulative distribution function, or inverse transform sampling in a nutshell. It's a very powerful method because as long as I can generate the inverse Cdf corresponding to the PDF of the distribution that I wish to sample from, then I can generate samples according to that PDF. The only complication arises because of the degree of difficulty involved in evaluating that inverse Cdf. Now, in the case of the Gaussian, it's a fairly long formula. In the case of other distributions, and the most notable of these is the exponential distribution, which we will see in the next video, those formulae can be significantly simpler. So this is a very important class of methods, the inverse Cdf method, and you should try it out.